So, very good evening, everyone. And so you are now in lecture 6, lasers and LED. So some of you master students, you are taking RRR 6032, and PhD students, you are taking 8032. So this is applied nanoelectronics. So my name is Associate Professor Dr. P. Susthitha Menon from IMEN, UKM. And just some introduction about myself. So I studied fully in UKM, my Bachelor of Engineering, my Masters, and also my PhD in UKM. Can all of you hear me?
Yes,
Okay, all right. So I joined IMEN in 2009 onwards. Since then, I have supervised 6 master students, 18 PhD completed. 4 PhD students are ongoing and 3 master students are ongoing. So I think in this class I have 1 master student, Rex Low. He's a student co-supervised by myself, Dr. Dila, and also Dr. Amri. Hi, Rex.
Hi, Doctor.
Okay. So I'm also co-author of 2 book chapters, more than 180 international journals and index proceedings. And my current research projects are in plasmonics, quantum electronics, also nanophotonics, biophotonics. I'm also working on optoelectrochemical sensors. And in the past, I've worked on development of silicon, germanium, InGaAs, quantum dot PIN photodiodes, and also optical interconnects. Also, during my postdoc, I worked on the development of multi-quantum well long wavelength vertical cavity surface emitting lasers. This is a type of semiconductor laser. Also, some research on high-K material in nanoscale MOSFET. This is transistor, and also semiconductor optical amplifier in CWDM. Also, silicon on insulator-based micro-ring resonators, Mach-Zehnder interferometer for optical sensing. So my expertise is mainly on nanophotonics, SPR-based nanosensors, optical fiber-based, and also waveguide-based. Also in the fabrication and characterization of optoelectronic devices using spin-on diffusion. I also have expertise in finite element method-based numerical analysis, mainly using Silvaco, numerical, and also COMSOL. I also have experience using fractional factorial design and also Taguchi method. So currently I'm seeking for full-time masters and PhD students for plasmonics-based projects. So if you have any contacts, your friends, your family, your relatives who are interested, you can ask them to drop me an email at susi@ukm.edu.my. Okay. All right. So we move on to our slides for today. Okay. So basically, I will cover introduction, lasers, LED, plasmonics, and LiDAR. Can you see my mouse?
Yes.
Okay, all right. Okay, let's see how many are in the class now. Okay, we have 12 out of 17. Okay, all right. Who's not in yet? Abe is not in? Okay, Abe joined as a guest. Dilip is not in. Eliani, Nashifa, Rajat Zaman, and Shaza not in yet. Okay, I hope they'll join us later. Okay, I'll move on. Okay, so introduction, just some brief introduction about artificial intelligence, 5G, and also IoT or Internet of Things. So this is a paper taken in 2018. So basically it shows 5G intelligent IoT to process big data intelligently and to optimize communication channels, and includes the processing center, object processor, and also sensing regions. So it is based on a 5G cellular network. So basically you have the internet and you have things, all right? Things means like sensor and so forth. And then you have intelligent. When you overlap all these 3 together, you get this 5G, and currently now it's upgraded to 6G, intelligent IoT. So in terms of the architecture, you can see here that in the middle here is the processing center, and you have the object processors, or we call it the base stations, and the sensing regions are around here in the 3rd layer, And finally, you have various types of application which are using this artificial intelligence, 5G, 6G, and also IoT. For example, education, transportation, healthcare, and so forth. All right, just to give you some introduction. So in terms of forecast for Internet of Things, it is estimated that around 29 billion connected devices are forecasted by 2022. Okay, this bar over here, of which 18 billion will be related to IoT, which is divided to wide area IoT and also short range IoT. Okay, so in due time, mobile phones are expected to be surpassed in numbers by IoT devices, which include connected cars, machine, meters, wearables, and also other consumer electronics. Okay. Look at the top 10 IoT segments. So basically you have smart city, connected industry, connected building, connected car, smart energy, and others. And in terms of regions, you can see that Americas and Europe, okay, this is prior to the pandemic. So now maybe this percentage may be not valid, right? 2018, right? And you can see that in APAC, the percentages are low, which means that it will pick up very fast from now onwards. Okay. In terms of applied nanoelectronics, photonics is one of it. And in terms of photonics overview, it can be said that the photonic market is growing year by year, where in 2023, the CAGR is expected to reach 780.4 billion. All right, this is in billion. And Asia Pacific region is projected to grow as the fastest among during this forecast period. Okay, there are other regions, North America, Europe, and so forth, but the largest chunk comes from Asia Pacific, the green one. And in terms of photonics overview, so the trends in photonics such as LiDAR, which is something that I'll cover today, and also additive manufacturing, this is covered by Dr. Abang in another lecture. And you can see that silicon-based photonics application, for example, hybrid silicon lasers. I think this one covered by Dr. Dila before this in the previous lecture. And it also says that technological advancement in light-based technologies, it has been driving a new wave of innovation. So in terms of application, the photonics application, and also in terms of geography. So photonics as an applied nanoelectronics area is fast becoming the trend in technology applications. Okay, and in terms of relation between photonics and Internet of Things, we have this Li-Fi LED luminaire, where you can see here the LED light can be used for Li-Fi light. You know, now you have Wi-Fi, right? Wireless internet. This is Li-Fi, using light for internet purposes. Where else than giving you light, it also can collect your digital information, and it can be transmitted through a power cable to a server and switch. So when you're sitting under an LED light, the Li-Fi enables bi-directional transmission of data through a modulated LED light beam. Okay, so you have an adapter, similar like your wireless adapter, and it's connected through a USB. So it receives the data from the luminaire and re-emits the signal to the point of access via an infrared beam. But this is only for short distance. That means when you move from this LED to the next LED, you'll be connected to this LED. Okay, so this is photonics and also Internet of Things. All right. Okay, so we move on to the subject matter, which is lasers. Okay. And the nature of light is such that you have the electromagnetic spectrum. So it ranges from the gamma ray, which is at 300 eta hertz at 1 picometer, the wavelength, and the energy is very, very high as 1.24 mega electron volts, right until the extreme low frequency, which is at 3 hertz. And you can see the wavelength is very huge. It's at 100 megameters. And the energy is very low at 12.4 femtoelectron volts. Okay, and you can convert the photon energy E, which is given in joules. All right, you can convert it to the wavelength lambda. So this energy E can be converted to the wavelength, and you can also get the frequency of the particular spectrum. Okay, so this is given by E equals to hc over lambda. And the visible light spectrum, it occupies only a small portion of the overall electromagnetic spectrum, so which is only from 400 to 700 nanometers, okay? And we are interested in this region and also the adjacent regions, which is the ultraviolet and also the infrared. Why? Because it is easy to generate them and also to detect them. So what's the meaning of generate? It is to make lasers and also LEDs, and detect means to create photodetectors and also solar cells. Okay. So there are two primary sources of light. One is laser, and laser is the short form for light amplification by stimulated emission of radiation. And there can be two types of laser, two or more. So there are gas lasers and solid state, also many other types. And also light emitting diode, which is the short form for LED. Okay, so we'll cover both these in this lecture today. Okay, if a short history of laser. So in 1917, Einstein, he was the first to have some research on the quantum mechanics of radiation. And in 1954, Towns, he was the first person to invent a maser. Now, a maser is using a microwave amplification of light. And finally, in 1958, Scarlo and Towns, they invented the laser. And in 1964, Towns received the Nobel Prize in Physics for his discovery. Okay, so Menon was the first to build the working laser. And moving on, you can see many other important names in laser: Goldman, Bell Laboratories, Myers, Yamamoto, and so forth. And from 1990 onwards, the laser has been widely applied in many other fields, including medicine, dentistry, and so forth. Okay. So recently, the Nobel Prize in Physics, especially in Photonics, in 2018, it was given to this group of people: Arthur Ashkin, Gerard Mourou, and Donna Strickland. So what was the Nobel Prize for? It was for the groundbreaking invention in the field of laser physics. Now, what did they discover? They discovered high intensity ultra short laser pulses, and we call it chirped pulse amplification. What is that? It is just laser pulses, which is normally used for medical technology. For example, in LASIK, you know, if you have cataract and you want to remove your bad part of your eye, you use laser. Okay, so this, they received the Nobel Prize. Okay, laser, the atomic transition in a laser occurs via stimulated emission. What does this mean? One photon which hits the active region produces two photons with the same properties. Okay, so you have the band, the conduction band and the valence band inside the active material. So what happens is a photon hits this active region, and you have the electron, it's sitting in a higher energy state. And when it moves to a lower energy state, you have emission of light. So it is stimulated because you have to induce the electron to go up to a higher energy state, and then it goes down to a lower energy state. So one photon can stimulate the generation of two photons. So we call it stimulated emission. Okay. So this is absorption. It is for detectors, which is covered in my previous lecture in fundamentals of nanoelectronics. So basically it is the opposite. Here light is, here electrons and holes recombine to give light, and over here is the opposite. Light is absorbed to create electron and hole pairs. Okay, it's absorption, here is emission. So how does inversion of energy level happen? So this shows the population density of the device or the active region versus the energy levels. So majority of carriers will sit in the lower energy level, all right, because that is the equilibrium. So what happens is, by stimulating, we can reduce the population over the lower level, and we increase the population of electrons in the higher energy level. But this higher energy level is not stable, all right? It's not stable, where the light will, the carriers will need to go down to a lower energy level to reach equilibrium. So what happens is, so we stimulate to a higher level, which is level 3, and then what happens is it's relaxed to level 2, and then because this is not a stable level, it will go down to a lower level, which is level 1. So during this transition from a higher energy level to a lower energy level, light is emitted out. So due to the conservation of energy, the movement of electrons from a higher energy level to a lower energy level produces light emission. Okay, so this is in a helium neon laser. So you have 3 levels. So this is the level 0, which is for helium. Level 0, we pump it to level 3. So what happens is due to relaxation, it goes to level 2, which is a metastable level. So this is in neon. So you have helium atoms, and you also have neon atoms inside the helium neon laser. So in level 2, the light will go down to level 1 to reach equilibrium, and during this transition, you have a helium neon light emitted out. Okay, so the N2, which is the higher energy level, the number of carriers in the higher energy level, it is N2, it is larger than N1. So therefore, you have a transition from higher energy level, the N2 will go down to N1, but we must amplify the intensity of the beam. So you have photon emission out, but how do you amplify that light? So we use mirrors inside a laser. You have mirror 1 at the bottom and mirror 2 at the top. It can be bottom and top, or it can be left and right, depending on what kind of laser. Edge emitting, it is left and right. If it is a surface emitting, then it's top and bottom. So this setup, the intensity will grow up to infinite. So what can we do to obtain the laser beam? So basically when the light is emitted here, so you have the light oscillating between these 2 mirrors. So it keeps on oscillating until the intensity increases and light is emitted out through one of the facets or one of the mirror. Okay, so you have the active medium. All right, this is the area where the population inversion happens, where, you know, for example, helium neon. So the population inversion happens here, and where we excite, the excitation mechanism also occurs here. We pump it to a higher energy level, and light goes down to the lower energy level, and you have photon emitted out. So when the photon is emitted out, it oscillates between these 2 mirrors. And these 2 mirrors are made in such a way that one is totally reflecting, 100% reflection, but the other mirror is only partially reflecting, less than 100, maybe 96 or 95%. So we call this a laser optical cavity, or in other words, it's also called a Fabry-Perot-Italon. So the photon keeps on oscillating in this cavity or this hole until it gets enough energy to be emitted out through this partially reflecting mirror. Okay. So this shows the example. So this is the beginning. You have stimulated emission. So you only have 2 photons. This is just an example. So 2 photons. So it hits the output mirror, and then it's reflected. It goes to the back mirror. So now you see 2 has become 4. So this 4, it hits again. So when it goes through the active region, 4 becomes 8. So it hits here and then it goes back. So now 8 becomes 16. So it hits back here and back and forth until you reach the equilibrium state where the photon gets enough energy to be emitted out through the partially reflecting mirror. So I hope it's clear to you how the laser excitation happens. Okay. So if you look at laser, we have these longitudinal cavity modes. All right, you have these modes over here. Sorry about that. Okay. And for a gas laser, for example, a gas laser, you have this laser cavity, which is this cavity here. This length of this cavity can be as large as 1 meter long. All right. And the frequency is about 150 megahertz between one mode to the other mode. We call this the cavity modes, right? Over here, the cavity modes, the number of modes which are propagating inside the cavity. And what we can do is, in order to get a single longitudinal mode in the cavity, we have a mode separation to exceed the transition bandwidth. So we can put an additional bandwidth here, and so you can get a single longitudinal mode. So this will become the single laser emission spectrum. Okay. Okay. And you can have a transverse mode. This is a 00, the basic mode for the laser. And else than that, we can also have other transverse modes depending on the application. Okay, but this is the most commonly and widely used, the 00, TEM 00. In terms of a Gaussian beam profile, so you have, this is the electric field amplitude, which is given in volt per meter, or the intensity of the light. This is what you can see from a laser, you know, like a laser pointer. And this is the spectrum, right? So it's highest, it's in the form of a Gaussian beam. So it's the highest in the middle, and this is in terms of position. And away from the middle, it becomes dimmer. Okay, what are the methods to excite the emission of photons? So one of the method is using flash lamps or also other lasers. So this is generally used with dye lasers and also solid state lasers. So basically you have a helical lamp inside here, all right, and also a laser rod for emission. And then you can also have a linear lamp and also a laser rod. So cylindrical quartz tubes with metal electrodes mounted on the ends filled with a gaseous species. You fill up with gas, and a voltage is applied across the electrodes of the flash lamp, and the current flows through the gas, produce populating excited levels of the atoms, and you have intense light emission. Okay, and the process is similar to that of electron excitation of lasers, except that a population immersion is not produced and the radiating material of the lamp radiates via spontaneous emission. So basically for optical pumping, you do not have the you do not have the population immersion. I mean, in the optical pumping, you have the population immersion, but if you're using electron excitation, you do not have this population immersion. The electrons and holes, they recombine to produce the emission of light. Okay. So else than optical pumping, some of the active mediums that can be used are helium neon, helium cadmium. You also have copper vapor lasers. Also, we can have molecules, liquids, dielectric solids, and also semiconductor materials, which, for example, is gallium arsenide and also indium phosphide crystals. Okay. So the gain medium can either be a gas, it can be a liquid, a solid, or even plasma. All right, if you go back here, all right, this is the gain medium over here where the emission occurs, or rather over here, the active medium. So it can be a gas, it can be a solid, it can be a liquid, or it can be a plasma, all right, to form the photons. Okay, so there are various mechanisms. And the light generated by stimulated emission, it is similar to the input signal wavelength, the phase, and also the polarization. That means it is coherent. And the optical cavity or the Fabry-Perot étalon, we call it the cavity resonator. It is a coherent beam of light between the reflective surfaces. It passes through the gain medium more than once. So the minimum pump power needed to begin laser action or the lasing threshold, the gain medium will amplify the photons passing through it regardless of direction, and only the photons aligned with the cavity manage to pass more than once through the medium and so have significant amplification. So basically it is saying that all these photons, they must be coherent with each other. The same amplitude, same phase, and same modulation. Then only they can laze out. They are similar. Okay. Okay, in terms of operation, we can have a continuous constant amplitude output, or we call it a CW or continuous wave. For example, you can have a CW dye laser with a broad range of wavelengths. Else than that, you can also have pulse or Q-switching. So this is what they got the Nobel Prize for pulsed laser. And this pulse laser, it can produce a high peak power because you can also do mode locking. That means you can use extremely short duration pulse, picoseconds. So you just imagine it is in picoseconds and the power is very, very high. And also you can also do it in femtoseconds, 10 to the power of minus 15 seconds. You can also have a gain switching pulse laser, and all these can produce very high peak power at a particular wavelength compared to the continuous wave. So continuous wave, the amplitude is the same, but this is pulses, right? Like bullets. It's like bullets. Okay, Q switching is sometimes known as giant pulse formation. So it is to produce a pulse output beam, or we call it a short pulse. And this Q switch is sometime of, it has a variable attenuator inside the cavity or the fabry-paro-etalon. So initially the laser medium is pumped while the Q switch is set to prevent feedback light into the gain medium. After a certain time, the stored energy will reach. So you have the gain over here, the blue color is the gain, and this is the resonator losses. So after some time, you can have a pulse coming out from the laser. Okay, so just one pulse, and then after some time you get a second pulse, and this pulse is very high in power. Okay, and you can see when the pulse is emitted out, there's a drop in the gain. So else than that, we can also have an acousto-optic Q-switch, which is you have a RF power into the active region. Okay, and this can give you a repetition rate of 0.5 to 5 kilohertz. So basically, is you have the laser medium, but it's also connected to an acousto-optic Q-switch. So when the RF is on, you have when the RF is on, it interacts with the material over here, okay, where light can be diffracted and also scattered. And then when the RF is off, the laser interacts with this acousto-optic material to produce a laser with different repetition rates. So you can have an acousto-optic quantum switch. What are the normal properties of a laser? So the most important thing is it is monochromatic, or we call it monochromaticity. What is the meaning of monochromaticity is all the photons has got the same wavelength, it has got the same polarization, and it has also got the same wavelength, same polarization, and the same polarization, wavelength, and what's the other one? Coherent, right? Same is coherent. All the photons are coherent. Okay. So for example, you have a helium neon laser. The wavelength is 632.5, and it can differ by about 0.2 nanometers only. Not much difference in the wavelength, right? It's monochromatic. So you can see that the beam is almost Gaussian in nature. Okay. And if you compare the wavelengths between, this is for blue wavelength and this is red wavelength. So this is 1 lambda, right? One sinusoidal sine gives you 1 lambda. And blue laser has got higher frequency than a red laser. And you can see that, of course, the wavelength is shorter, right? Blue is about 200 to 400 and red is about 600 something, okay? So else than monochromacity, it also has directionality. So this is a conventional light source, right? It can be a lamp, an LED or whatever. You can see that the light is propagating all over the place. Whereas in a laser, it is highly directional beam. It only emits in one direction. And you can see upon emission, this is the beam width. And after some time, there is a divergence angle, theta d, but it's not so much difference compared to the conventional light source. So this beam divergence from here to here, from upon emission, we call it near spot and far spot. This is given by theta d equals to beta lambda over d, where beta is 1 depending on the light amplitude distribution, lambda is the wavelength, and d is the beam diameter. Okay, so this is directionality. So it is monochromatic, it is directional, and it is coherent. Okay, incoherent means you can see the amplitudes are not similar, whereas in lasers, you can see the amplitudes are similar, all right? And laser light, it cannot be perfectly monochromatic, it cannot be perfectly directional, but it is perfectly coherent, okay? However, laser light is far more coherent than light from any other source, okay, compared to any other light sources. Okay, so you also have laser divergence. We saw that just now. So when light comes out of a laser, you have what we call the beam waste over here. And after some times, it diverges out. All right, and we call this the Rayleigh length. After some time, we call this the Rayleigh length. And finally, this is the beam diameter. So if this is a laser light, okay, this is at half angle and this is at full angle. And if you have a detector over here, this is what you will see. And we call this the beam diameter. You can see that it is a Gaussian profile of a single mode laser beam. Okay. All right, what are the different types of laser and its operating principles? So the first, we have a gas laser. This is a helium neon laser. Its operation wavelength is 632.8 nanometer and it is a continuous wave. There is no pulse, all right? The light just keeps shining. And the gain medium over here, the gain medium is a mixture of helium and neon gases. And what is the pump source? It is electrically pumped. Electrical discharge of around 1000 volts between the anode and also the cathode. So it is electrically pumped. Okay. Solid state lasers, it is commonly made by doping a crystalline solid host with ions that provide the required energy state. So this is, for example, a neodymium YAG laser. YAG stands for yttrium, aluminium, and garnet. So it produces very, very high power in the infrared spectrum at 1064. The frequency can be double, triple, or quadruple to produce 532 nanometer, which is green, visible light, 355 nanometer, which is ultraviolet, and 266 nanometer, which is also ultraviolet. So this is how a neodymium YAG laser looks like. Okay, more about neodymium YAG laser. So it is transparent and also it is colorless. So basically it is doped with about 1% of neodymium ions into the YAG crystal, and the crystal color then changed to a light blue color. Okay, so this shows how the pumping is occurred from E1 to go to E2, then it's pumped up, optical pumping, it's pumped up to E3. And then what happens, you have a relaxation going down to E3, and finally it will move down to E2 with a laser transition of 1.06. Okay, so this is how it works. You can also have a ring dye laser. This uses organic dye as the gain medium. So the wide gain spectrum of available dyes allows this laser to be highly tunable or to produce very short duration pulses. So in the order of few femtoseconds. So some of the dyes that can be used are rhodamine, fluorescein, and so forth. Okay, so this is using a dye. So basically you have the dye over here. Okay, you have the pump laser. So it's optical pumping over here. And then you have the tuning mirror, and this is the etalon. And you can have the light emitted out finally over here. Okay, so this is the ring dye laser. Okay, the most famous is a semiconductor laser. So the active medium is a semiconductor and it emits wavelengths ranging from ultraviolet 375 up until 1800 nanometer infrared. So low power laser diodes, it can be used in laser printers, in CD and DVD players also. More powerful laser diodes frequently used to optically pump other lasers with high efficiency. Normally it's used as a pump to pump the lasers. Okay, so just some theory, some physics. So basically, for photon to be produced, you need to have recombination of electrons and holes. So this occurs in the semiconductor junction. So this shows the circuitry of a laser. Basically, it comprises of a P-type and also an N-type junction. And in terms of the conduction and the valence band, without the presence of voltage, you can see that the electrons are holes are in their respective P and N regions, and there is a huge barrier over here. Okay, so they cannot freely move to recombine. So in order for photon to be formed, carriers need to recombine. Electrons need to recombine with holes to produce photons. So we provide a forward voltage, and with this forward voltage, you can see that this barrier is reduced, and electrons and holes can recombine, and recombination causes emission of photons. So in terms of the layers, so there are two things happening here. The first is the movement of the electrons and holes, and the second is for the photon, right? So this is electrical part, and this is the optical part. So let's look at the electrical part. So you have the active layer. Remember the cavity, the etalon. This is the active layer. So in this case, it is N indium gallium arsenide phosphate. So you can see that the band gap energy is 0.95 electron volts, and you can see that this band gap is low. So it is low so that electrons can recombine with holes over here. And you can see that the adjacent N and P type indium phosphate, P indium phosphate and N indium phosphate, and the band gap energy is higher, 1.35 electron volts. So this higher energy band gap is because we do not want, we want the electrons and holes to move to this active layer so that recombination occurs in the active layer. Okay, so it's a barrier. We do not want them to move out from the active layer. So holes and electrons are injected, right? Because you have a forward voltage, so they move to the active layer. So these are called electron and hole movement to the active region. So it's called carrier movement. And when they recombine, you have emission of photon. Now, how do you protect this photon from escaping out from the active layer? Remember, you need the photon to remain in the active layer because you need to oscillate the photons in order to produce the laser beam. Remember, one becomes two photons become four, population inversion. So in order to maintain the photons in the active layer, what needs to be done is we need to play around with the refractive index. I think in Dr. Abang or Dr. Dila's class, you would have learned about total internal reflection, where if you have a material with a higher refractive index coupled with a material with a lower refractive index, what happens is photon is contained. It cannot escape, right? You have total internal reflection occurring. So the photons, they cannot escape out because of this optical structure. You have a higher refractive index coupled to lower refractive index. So electrons and holes need to be managed using the band gap, and photons need to be managed using the refractive index. So there are two mechanisms in a laser for optical emission. So this is a laser, aluminum gallium arsenide laser. You can see that when the stoichiometry, the aluminum mole fraction is changed, there is a difference in the band gap energy. You can do band gap engineering to produce different band gap energy which corresponds to different wavelength. So depending on the application, you can dope the material accordingly to produce the wavelength that we want. Okay. All clear? Understand? All sleeping, is it?
No.
Doctor, regarding the heterojunction, is that like, do we need to do some Fresnel reflection to reflect back the light within the active layer?
Come again, Rex?
Yeah, this light heterojunction.
Yeah.
Do we need to do some activity like Fresnel reflection in order to reflect back the light?
No, this is, Rex, this is just the selection of the material. And also, yeah, sometimes we have what we call the bright mirror. We put in some bright mirror.
Yeah.
Yeah, bright mirror. So you cannot suddenly have a jump like this. So you have a bright mirror such that in total, the active layer refractive index, the effective refractive index is higher than the adjacent layers.
Okay.
So you have we call it bright mirrors.
Okay, doctor.
Okay. All right. Okay, so we looked at different types of lasers. Now we come to fiber lasers. I think Dr. Abang also covered in his slides. So fiber laser, you can have so it is guided because of total internal reflection in an optical fiber. So you have a double clad fiber, high power fiber laser. This one is normally for telecommunication purposes. You also have a fiber disc laser in the form of a disc, and the output of this fiber laser is typically 100 watts to more than 1 kilowatts. Okay. So other types of lasers is a chemical laser. So it involves a chemical reaction. It also can achieve high power in continuous operation. Hydrogen fluoride laser, it is more for infrared and the output power in megawatt. Excimer laser, it is powered by chemical reaction, involves an excimer. So an excimer is actually a short-lived dimeric or heterodimeric molecule formed from two species. So typically to produce ultraviolet light. So these are some excimer noble gas compound, arganium fluoride and so forth. For
Doctor, I can't hear your voice.
Sorry, doctor, we can hear your voice. Hello, doctor. You also can hear our voice? Doctor.
Doctor, we can't hear.
He's. Oh.
What?
Doctor, we cannot hear.
I think she. It's her phone. Eh?
Rex, I guess you have to alert her.
Yeah, I go find her.
Thanks.
Doctor, we cannot hear.
Presenting. Hallelujah.
Doctor, I don't hear anything.
We are not hearing anything. Please, sound, please.
How about everybody request control?
I have long time don't hear anything.
Can you hear me now?
Yes, doctor.
Yes, doctor.
Yes, doctor.
Yes, doctor.
Oh my God, you're so much behind time. Okay.
Yes, doctor.
Okay, we move on. Any question about laser? So if not, we move on to LED.
To LED. Okay, so laser is a stimulated any emission, and LED is related with a spontaneous emission, right?
Yes, correct.
Okay, so I have some questions about the laser because I don't differentiate with gain medium and active medium. And what is the
They're both the same.
Gaussian?
Active
Same.
medium and gain medium are the same thing. Basically, the active medium emits photons, and the gain, why we call it a gain medium is because photons oscillate between the mirrors, and during oscillation, one photon becomes two. You have a increase in the number of photons, right?
Yeah.
So that's why we call it a gain, because
Yeah.
one photon becomes two, two becomes four, four becomes eight, and so forth.
Used as feedback mechanism, right?
Yes,
So,
correct.
So, and what is the relation with this cavity? This reason, when we use mirror for gain mechanism, and that area called cavity.
A cavity is a hole.
Okay.
Where the photon movements occur, right?
Okay,
Hole,
okay.
not a hole, but it's an area where the photons oscillate, right?
Okay.
While they are oscillating, they pass through the active medium, right? They pass through the active medium many times. Each time when they pass through the active medium, one photon becomes two, two becomes four, you have emission of light, stimulated emission. Each time a photon passes through the active medium, stimulated emission occurs. And when the photons hit the mirrors, you have oscillation of light. And since you have one becomes two, two becomes four, and so forth, there is a gain, right? There's an increase of power.
Oh, okay. So this is the transition. I can tell third level or fourth level transition when the electron transfer from matter state from to the ground level, and
Yes.
at the time there are a flow of a whole positive side. And is that related with something with cavity?
Yes, it has to occur in the cavity. It has to occur in the cavity. You see, if I can make it a bit clear over here, yeah. So this is the cavity. It's not a physical hole. It's just an area where the active medium is. What is the active medium? The active medium is where the population inversion happens, where electrons and holes recombine to produce one photon. And one photon will stimulate another two more photons to be produced. Remember, it's stimulated emission, right?
Yes.
So one photon will produce two, two will produce four, and so forth. All this happens in the active medium. And you can see from two, and then when it hits the mirrors, so when they go through the active medium again, you have more stimulated emission occurring, right?
Yeah, at the time we get the light.
Yes, then you have what we call gain. You see, from initial two photons, you get so many photons. So we call this a gain, right? Gain.
Then
Increase.
we get coherent emission.
Yes, correct.
Okay. Still cavity still have some. I have to maybe study more about cavity. I get some basic idea.
Area. It's an area. Cavity is an area where the active medium is.
Okay,
right?
so cavity resonator.
Cavity resonator means an area which is bounded by two mirrors or two resonators, right? So for example, in this weak cell, over here, so this is the cavity. So you have, this is the cavity.
I don't
between
see
the
the
mirrors.
slide.
You can't see. Oh, I'm sorry. Okay. Share content, screen. Can you see now?
Yes, Prof.
Yes, doctor.
Okay, so the cavity is simply the area between the mirror.
Okay.
So you see when the photon is emitted from the active region,
Okay.
so one photon produces two photons. So two photons hits top mirror, and then it comes back to the active region, 2 becomes 4. Now 4 hits the bottom mirror. When they go up again, 4 becomes 8. So it hits
Okay.
up, down, until they gain enough power to be emitted out. You see, in terms of if you look at the power and current, so initially this is the oscillation occurring. So then they have enough power to be oscillated out. So you have a laser emission out.
Okay, so this yellow part is act as a mirror, and the middle part is a active medium or as a cavity.
Correct. Cavity means the area between the mirrors.
Okay.
Which contains the active region.
Okay, and the time we get that resonator also.
Correct. Resonator is just an area where light is moving, oscillating. Yeah.
Okay, at that time. Thank you.
All right. Any other questions? Okay, it's 3:30. I still have many slides to cover. All right, we move on to LED. So similar like laser, the LED has also won a Nobel Prize in Physics. This is in 2014. So a group of Japanese scholars, Isamu Akasaki, Hiroshi Amano, and Shuji Nakamura. So their Nobel Prize is for the invention of efficient blue light emitting diodes, which has enabled bright and energy saving white light sources. So from blue LED, they produce white light source. So basically they use phosphor, right, to get this white light source. So we'll cover that after this. So basically an LED is similar like the laser. You have a PN junction. So when it's forward biased, you have charge carriers, electrons and holes. They flow into the junction. So when the electron meets a hole, it falls into a lower energy level and releases energy in the form of a photon. So it's the same like a laser, only thing there is no stimulated emission. This is spontaneous emission, right? It's spontaneous. So the wavelength of the light emitted and therefore its color is dependent on the band gap energy of the PN junction. And in indirect band gap materials such as silicon and germanium, the electrons and holes recombine by non-radiative transition. So this one is what Dr. Dila presented just now on defect engineering in silicon. The purpose is to produce silicon laser lights, but the recombination occurs through non-radiative transition. Okay, so just now laser is through stimulated emission. LED is spontaneous emission, where there is no external stimulation, there is no optical pumping, there is no electrical pumping and so forth. So why the light is emitted out is because of the nature of the medium, the active medium. It will emit light when you provide it with a forward bias. Okay, this is a LED. Okay, and these are different types of colors of LEDs. And same, you have a PN junction, and you can see when the electrons and holes recombine, light is emitted out. Okay. And this shows anatomy of an LED. So basically the semiconductor is resides over here, and you have an anode and also cathode. If you notice, the anode leg is longer than the cathode leg. This is the way to differentiate the legs of a LED. And else than that, you can see that in terms of the LED, you have the bonding wire for the anode and also the cathode. And you have the lead frames coming out, and it's covered by an epoxy dome. All right, over here there's an epoxy dome. So light is emitted out from this semiconductor, and this shows the different layers inside the semiconductor. Basically, it sits on a silicon substrate. You have P-type germanium, and the N-type is using germanium, and the topmost layer is using silicon dioxide actually. And this is the back contact and this is the signal contact. This is the actual fabricated device. This is the back contact and this is the signal contact. And light is actually emitted out from this region over here. Okay. So it is on an N-type substrate. Yes.
Doctor, in this light emitting diode, what is the size of this diode? In that way,
what is the size of the diode?
Yeah, this place between anode and cathode.
Between anode and cathode over here, you can see here it's about 2 microns. So yeah, so it's about 4 to 6 microns.
Okay.
Yeah, you have the dimension given here.
Okay. Thank you.
Okay, so it's built on an N-type substrate, and the refractive index of the packaged material should match the index of the semiconductor. So otherwise, the produced light gets partially reflected back. So there are two mechanisms here. You have the light is emitted out from the LED. So the first is you need to look at to make sure that this light escapes out from the dome lens. So we need to choose the correct material so that when light escapes out from the semiconductor, it does not get reflected back as heat. So the selection of material inside the dome is important. As you know, if the refractive index of the packaged material should match the index of the semiconductor, otherwise light gets partially reflected back, or where it may be absorbed and turned into heat, thus lowering the efficiency. The refractive index of a material is the ratio of the speed of light in a vacuum to the speed of light in the material. So this type of reflection also occurs at the surface of the package if the LED is coupled to a medium with a different refractive index such as glass, fiber or air. So you need to take care of the type of material used. So most LED semiconductors using gallium arsenide or gallium nitride is about 3.7, the refractive index. So it's quite high. So in almost all cases, the LED is coupled into a much lower index medium. So you have high index coupled to low index medium. So the large index difference makes the reflection substantial, and this is usually one of the dominant causes of LED inefficiency, right? So you have a large mismatch here. And so how to counter for this? So it's emitted back as a reflection, LED package and also package air. So the reflection is most commonly reduced. So that's why you see LED has got a dome shape. The purpose is to reduce the reflection. Why? So as you know in Snell's law, if light hits two different mediums at an angle, light gets reflected and refracted. So you lose the light. But when it hits in perpendicular motion, you get the light not reflected and also refracted. So that's why in dome shape, you see when the light hits the dome, it is normally in perpendicular motion. So you can reduce the amount of light which is reflected and also refracted. Okay, so this type of reflection also occurs at the surface of the package. Okay, this slide I'm done. So therefore, it's dome shaped. So the angle of reflection is minimized. So else than that, an anti-reflection coating can also be added. Okay, so this is Snell's law. Okay, this shows different LED materials and the subsequent wavelength. So from 400 nanometers right until infrared 760. So many different types of material, and all these have different colors, different materials, and also different forward voltage. Right, this is at 20 milliampere. Okay, if the emitting layer, if it's not a semiconductor, but it's using an organic compound, then we call it as an organic light emitting diode or an OLED. And this OLED, it can be also made from polymer materials, which are flexible, such as PLEDs, polymer LED, or FLED, flexible LEDs. So one of the major application of OLED in TV screen, this is an OLED and this is in a LED TV. And if you look at an LED TV, you have the, it is a complex structure. because you have the backlight unit, you have the CCFL, and also the LED. And the lighting unit is determined, given by the pixel unit. Whereas in an OLED, the structure is simpler. Okay, it is simpler and it's self-emissive, and the lighting unit is also defined by the pixel unit. So this shows an OLED structure. So instead of a semiconductor emitting layer, you have an organic molecule or a polymer as the emitting layer. And now OLED is becoming very famous in smartphones, handheld game consoles, and also in PDA, and also being used in solid state lighting applications. So you can see OLED televisions are thinner compared to LED TV. Okay. And polymer LED, they are lightweight, they are flexible, and the applications can be many, and also to make displays. Okay, so basically you have a polymer layer as the emitting layer instead of a semiconductor or a die. Okay, so you have a polymer layer. And if you compare for smartphone display technology, this is for BlackBerry until Galaxy. So different technology are used to produce the imaging layer. So you have a LCD, liquid crystal display. This is thin film transistor. And moving on until AMOLED, this is active matrix OLED. And you can see that the technology also improves from first generation to fourth generation. So for first generation is outfolding, and then second generation you can have infolding, and the third generation is having infolding still. This is in 2019. And I think coming soon or already in the market, you have the fourth generation, you can fold in and out multiple times, right? So this is the technology that can produce using OLED technology. Okay, now how do you get a white LED light? So basically, you have the LED chip, and then the blue light is emitted using the corresponding active material. So by applying a yellow phosphor layer, it converts the incoming light into red, blue, and green. So as you know, the combination of red, blue, and green, it produces white light. Okay, and this shows different types of LED or different types of lights over the years, right? This is a year, and this is in terms of the efficiency, in terms of lumen per watt. So you can see way back in 1879, we have the light bulbs. And you can see the efficiency until now, 2020, is still very, very low. Whereas if you compare with vapor lamp, fluorescent lamp, halogen lamp, halide lamp, vapor lamp, fluorescent lamp, and finally LED, you can see the efficiency of LED is the highest among all the different types of lamps. Okay, so this started in way back in 1996, and you can see the efficiency is still very, very high now. Okay, that's why LED lighting is very famous. And if you look at the different lamp specification, so nowadays when you want to look at a lamp, you look at the power, which is giving you how much is the electrical load. You also look at the lumens, which is the brightness, how bright the lamp's light is. You look at the temperature, which is given in Kelvin. The warm-up time, how long it takes to light up. The dimmability, can you dim it or not? The shelf life, how long can you use it? The color rendering index, the energy savings, the mercury content, this is for environmentally friendly. And also the illumination angle, what is the shape and the range of the effective light. So you can have intelligent luminaires, right? So it can be switched on and off so quickly that is imperceptible to the human eye. So for example, in museums, so when it detects the presence of somebody, it can switch on, or in buses, aircraft cabin, and also in trade fair stands. So it's intelligent LED luminaire light. Okay. Now, what is the comparison between laser and also LED? So basically the working principle in LED, it is spontaneous emission. Therefore, it is using electroluminescence. And in laser, it is a stimulated emission. You need to have a pumping source. Okay. And in terms of form, LED, this is light amplification by stimulated emission of radiation. The response of LED is slow. Therefore, in telecommunications, it cannot be used for long distance telecommunications, only for very short distances. And for laser, it's very, very fast response. The driving current in LED is quite high compared to laser. And the nature of the emitted light is incoherent, you know. So the photons emitted are not coherent. Whereas in laser, it's coherent and also monochromatic. That's why you can have a very high power laser. The junction area in LED is very wide, right? That's why it can light up a whole room, right? The junction area is very big. Whereas for a laser, it's narrow and small. You can see here for a LED, the spectrum is very huge, whereas for laser, it's very sharp. So that's why it can go far. LED cannot go far. Okay, this shows incoherency. So laser light is coherent and LED light is incoherent. Bandwidth, so the bandwidth for LED is in the terahertz, but for laser it's in the narrow range, megahertz to 2 megahertz. The efficiency is only about 20%, but laser it can go up to 70%. That's why it's used in telecommunications. The numerical aperture, which is how big the light beam size, so it's higher in LED, so that's why it can cover a wider area. And for laser is extremely low. Okay, and the cost for LED is very low. That's for it's economical, but for laser it's high cost. That's why it's used in specific applications. Okay, so just a comparison between laser and also LED. Okay, if there's no questions, I move on to plasmonics. Any questions?
No, doctor.
All right, all of you are clear on laser and LED?
Yeah.
Okay.
Yes, doctor.
Okay, so just a few slides on plasmonics and LED and LiDAR. Okay, so plasmonic deals with the generation, manipulation, and detection of surface plasmon polaritons. So basically, SPP is the quasi-particle due to the coupling of light and also surface plasmons. And surface plasmon is electron oscillation wave at metal surfaces. Okay, so basically, this shows the frequency spectra of polaritonics. It's shown here. You have the Menon polariton from here. So basically, this is electronics and this is the photonics, electromagnetic wave. This is free charge current. This is phonon polariton. Phonon actually occurs in the lattice of materials. And surface plasmon polariton occurs is overlapping with the photonics region. You have exciton polariton and also surface plasmon. Basically, this occurs in the surface. So basically, it uses noble metals, plasmonic materials at optical regime. You can have gold or silver. And this shows a plasmonic resonance way back long time ago during King Lackage's time. So this is a glass which was viewed in daylight, and when you show light on the cup, you can see a reflection of light. So basically, what is in this glass is actually a gold nanoparticle is in the glass. It's about 70 nanometer in diameter, and the color response is different to that of gold in bulk, right? So the particles resonantly reflect green light over here, and strong absorbance around 500 nanometer and below occurs, right? So gold nanoparticles, plasmonic resonance, you can also see it in many different applications, right? For example, this is in nanoparticles in different nanoparticle sizes. It emits out different plasmonic light. And this shows in a church. So there are gold particles, it's emitting out different colors of light. So the field pattern of SPP, this is given in a 2D field distribution in X and Z. This is in X and Z. So it denotes the magnetic field and also the electric field. Okay, this is the simulated work. And basically, when you have light propagating through glass, so it just propagates through it, right? So because you have the total internal reflection, so light remains inside the high refractive index. Whereas in a metal dielectric layer, you have a negative dielectric for the dielectric layer, and so you have this interaction between the electrons in the metal layer and also the dielectric, and a field, we call it the plasmon field, is formed. Okay, so SPR causes a reduction in the reflectivity of the incident light. So you have light hitting a metal layer over here, and the light is also reflected back and collected by a detector. So what happens in this metallic layer is you have oscillation of electrons and holes, and this we call it electron gas. So this oscillation of electrons and holes over here, when it interacts with the incident light, when they are in resonance, when this electromagnetic light, incident light, is in resonance with this electron gas, you have a plasmonic field formed. And if you notice this electron gas formation, there is a distance covered by this electron gas. For example, if you're using silver, this length of propagation of light is about 22 micron if it's at 514 wavelength, and it can go up to 500 microns if you are using a higher wavelength, 1060. So there's a potential to use this electron gas effect for chip scale optical interconnects. Okay, so in bulk metals, the frequency, oscillation frequency is given by omega p, and the dielectric constant is 0. But in thin metal surfaces, this dielectric constant becomes -1, and if you use the Drude model to approximate, the oscillation frequency becomes omega p divided by a square root of 2. And if you're using nanoparticles, so this dielectric becomes -2, and using the approximation of Drude model, the oscillation frequency reduces even further, becoming omega p over the square root of 3. So this occurs in surfaces, thin surfaces. So in bulk, you cannot see this plasmonic effect occurring. Okay, so this is the angular frequency versus the wave vector, and you can see this shows the plasmon polariton in a normal material, and this is the wavelength of light, omega equals to ckx, photon in air. All right, the angular frequency for light. And what happens is when we damp this material using maybe a prism, when we damp it, we can change this surface plasmon into this red color over here. But still, the incident light does not meet with the surface plasmon. How do you make them meet? Is by using a prism, right? We use a prism to damp the propagation of light, and so you have an overlap of the surface plasmon electron gas surface plasmon polaritons with the incident photon. All right, and you have a field formed above the dielectric layer over here. So this plasmon field can be used for sensing purposes. And in my work, I'm using this Kretschmann configuration where there's no gap between the metal layer and also the prism. Okay, so basically you need to have a metal layer, a positive dielectric medium, which is air, glass, analyte, and so forth. You have electromagnetic wave, which is an optical wave. When the optical wave vector length, which is the incident light, is equal to the surface plasmon polariton in the metal layer, you have resonance occurring and a plasmonic field is formed. And this plasmon effect only occurs for p-type, or p-polarized light. Okay, it cannot occur for the s-polarized light. This is just because of the electric field direction is parallel to the light's plane of incidence. Okay. So there are many different types of configuration. You can have a Kretschmann, two-layer Kretschmann, auto, and so forth. But in my work, I'm using mainly Kretschmann configuration. So we have various research going on at IMEN in plasmonic field. We have an equipment, SPR equipment, and we have been able to successfully detect urea and creatinine with increasing molarity using the SPR Bionavis equipment. As than that, previous students have also looked at imaging of the plasmonic layer for different optical power and current. Also detection of uric acid, and also for glucose sensing. Okay, so some of the work done at Photonics lab. Else than that, we can also have a electrochemical biosensor using a chemical effect together with SPR. So over here, so else than having an optical effect, we introduce a voltage as well into the layers. And by doing a cyclic voltammetry, we can obtain both electrochemical sensing and also optical sensing. Okay. All right, that's for plasmonics. We move on to LiDAR if there's no questions. If you have your questions, I think you can email me or chat with me and ask me the questions. I'll be very glad to help you, or you can also WhatsApp or call me. I'll give you my phone number because I want to catch up with the time. Okay? Okay? Hello? Sleeping up?
Okay, doctor.
Okay, doctor.
Thank you.
Okay, doctor.
Big
I thought you all are
presentation.
sleeping already.
No sleeping, just hearing, just get to observe.
Okay.
The last
Just
part is too much high.
okay. Okay, just a few more slides, okay? Then there's a surprise waiting. So please wait until the end. There's a surprise. Okay.
Okay.
So we move on to LiDAR. Okay, LiDAR is light detection and ranging. So it is a detection system which works on the principle of radar, but it uses light from a laser. So you have, if you know this Google map, if you have seen the car going around, basically it's using LiDAR. It sends out light and it receives back light to get images of the area. And sometimes when you go to Google Map, you can see images of certain places. So all these images are loaded back. So mainly it's using LiDAR technology. So you can see LiDAR can also be used in a helicopter, and there's a laser equipped in the helicopter. So it sends out laser lights, and then the light is reflected back and images of the region is collected back, and you can get a view of what's happening in the region below you or something like that. Okay. And the LiDAR technology, the overview and the application. So basically it can be used in automotive for mapping and also ranging applications. So when two cars are going along in a road, or sometimes you can have a traffic light system using a LiDAR as well. Also, if you remember a few years back, we have the AES, you know, the summon system using AES is also using LiDAR. So basically the light will sense whether your car is speeding or not. They can even capture the number plate of your car. So this is used for automotive using LiDAR. For surveying and also civil engineering, also for terrestrial and also aerial scanning for Navy, for Army, right? They use LiDAR. So the requirements is there's a wide detection range, high accuracy, temperature stability, miniaturized and multi-sensor capability. It's also low cost and also low power. So basically it covers the visible region 390 until 700 nanometers. So you have a laser, a beam expander, and then this is the emitted light, and the backscattered light is collected by, you use a telescope and you have optical filtering, and you get back the image that is collected back. Okay, so basically you have a laser scanner here. It scans, as the helicopter moves, it scans different parts and it collects back the spectrum from here. So then they use some of the they use some software to plot back what they have observed from the collected spectrum. Okay, it's called a scanning infrared laser rangefinder. So this is LiDAR. Okay, so for active remote sensing, light is emitted, it is scattered and also detected. And since we know the speed of light, we can also measure the distance traveled. Okay, so this shows this figure is a bit blur, but basically it gives you, for example, in an army system, right? So for example, the Navy, they want to know whether there's any enemy or somebody is down here. They can use LiDAR to detect whether there's any people or anybody here that, or any equipment or something down here. Yeah, using the LiDAR. Okay, so this just shows more application of it. So you can have a passive sensor just on the surface, or active sensor which can go down further, give further details, deeper scanning. Alright, you can watch more in this video, LiDAR video, to find about the applications. Okay, now I will cover a few research works related to laser, LED, plasmonic, and also LiDAR. Just a few slides. Okay, so basically the optoelectronics market snapshots, you can see that lamps and image sensor are the largest contributor for the economic growth. All right. So in now we know we are all in the COVID problem. So this was published in 2020. So basically they use a light detector to detect this COVID-19 virus. So what you have is two systems. One is a Kretschmann SPR detector over here, plasmonic sensing. You have gold nanoparticles on top of the substrate layer. And else than that, there is also a thermoplasmonic laser at the top, right? And what happens is when you have a plasmonic field over here with the presence of the COVID virus and the presence of this the heat from this light over here, a specific thermoplasmonic field is formed. We call it LSPR response. When the virus is present, you get a peak, all right, because it interacts with the gold nanoparticles over here. And in fact, it can detect increasing molarity from as low as 1 picomolar until 1 nanomolar. So this is the concentration of the COVID virus. So this one was produced by Q in 2020. Okay, so this is one example of plasmonic detection of SARS-CoV-19 virus. So else than that, we also have electrochemical detection. For this is for MERS-CoV. So MERS, different type of virus, also using ECV, electrochemical sensing. You also can do an optoelectronic integrated circuit comprising of a laser and a detector. So you have a modulator over here. So if this region is exposed to any kind of analyte, so you can have a difference in the light collected, and this can be transmitted through the optical fiber as well. So you can use a LED, VCSEL or LD. The sensing area can be SPR, microring resonator or Mach-Zehnder interferometer, and also there is a detector comprising of a photodiode. Okay. Graphene-based optoelectronic. Graphene is becoming a popular material for optoelectronic applications. So for transmission, for LED, OLED, for energy harvesting, for DSSCs, for solar cells, and also for detection. So basically detection in a lab on chip, right? On the chip itself. Okay, can read up further from this Nature Photonics paper. We can also combine optoelectronics with MEMS. So this is an example of a label-free biosensor. Basically, you can see the wavelength of light changes when there's a deflection of the membrane over here. And this is using both a MEMS effect and also an optoelectronic effect. Okay, you can read up further from this paper over here. So this is a SPR-based sensor with a LED. So instead of a laser, you have a LED and you have a plasmonic substrate over here with the presence of a protein, right? The protein binds at the surface of the gold layer over here. And you can see after binding, the intensity of light reduces. So you know that's the presence of some kind of protein over there. Okay. Plasmonic laser, this is using a zinc oxide nanowire. And the emission wavelength occurs at about 372 nanometer, which is an ultraviolet wavelength. So zinc oxide nanowires can be used to produce lasers. Okay, that's it for my slides. Are you ready for the Kahoot quiz?
Hope so. I don't know.
Hello, everyone ready?
Okay, madam.
Yes, doctor.
Yeah, doctor.
Oh, this one is not official, okay? It's official quiz, but I just want to wake you all up because it's a boring lecture. So I just want to.
No, not boring lecture. It's too much informative.
Okay. So there's a first and second and third winner. So there's some monetary prize and also some certificates. So all the questions are related to whatever was in my lecture slides just now. So if you were paying attention, you can get first, second, or third. So are you ready?
Okay.
Are you guys ready?
How can we get this?
Yeah, how can we assess this?
Yeah, I will tell you, but I just want to know where everyone woke up or not. If you're sleeping, please wake up.
Not sleeping.
Not sleeping? Abe, you have any question?
Yes, doctor. I'm awake.
Yes, Abe?
Yes, doctor. Yeah, okay, I'm ready.
No,
Two
because you raised
minutes.
up your hand.
Oh,
Okay, ready? Okay. So
okay.
first of all, you need to go to kahoot.it. Okay, this is the 3D, this is the barcode you can scan. Go to kahoot.it. Are you guys all there?
Actually, I do not have any scanner of my mobile, so I can't do this.
You can also do it on your mobile. Do you have is your mobile connected to internet?
Yes, but I do not have any scanner in my.
Or you don't have a scanner, then you just go and type this in your Google.
Yes.
Okay, Google.
Type it out, kahoot.it.
So they need some code, game pin.
Yeah, you need a pin number, but I want everyone to go to Kahoot first. Are you in Kahoot yet?
Yeah, doctor.
Yes, doctor.
It's very fast, just a few questions only.
Doctor, they are asking code.
Pardon?
Hello.
Yes?
Hello. Hello.
Yes.
Madam, I did not see the link.
Oh, you didn't see the link yet. Okay, it's
Yes.
kahoot.it. Maybe I copy it and put it in the chat.
Okay.
Okay, it's okay, so it's already in the chat. You can click on it.
Doctor?
Yes? Yes? Okay, once you're already there, you have to put the pin number. Okay, so the pin number is loading now. Can you see my screen?
Yes, doctor.
Yes, doctor.
Okay. So try to get first, second, and third.
Doctor, what's the pin?
Doctor?
Yeah, it's loading.
Where is the code? I entered this. I did not get. They are asking about. Okay. Yeah.
Just hold on. Okay, that is the pin number 4427319.
4473 219.
Yes, doctor.
4427319.
21.
Okay, Shafika is in, Shifa is in, Rex is in. 4427319. Okay. Pin number is 442 7319. All right, 442. Rosnita, Bella, Revati, Shaza, Asif. Who's this? Who is 442 7319? What's your name? Arman. Okay. Who's
Muhammad.
442?
Muhammad.
Muhammad. Okay.
Yes.
One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 people. Let's see. Everyone in yet? You have 13 of you, but there's only 11 inside.
Doctor,
Yes. Yes. Anyone having any problem? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Another 2 more people. Who's not in yet? Who doesn't want to play?
Still sleeping or
Still sleeping.
then
Okay, we shall go ahead and start, okay?
Okay.
All right, are you ready?
okay.
Number 1, number 2, number 3, okay? Go.
Okay.
Laser stands for? You have to click the correct answer.
Is still loading.
Is not over
Oh, got
just
timing
yet.
one. Oh my god.
Now we
Time's up.
don't get the display, but is still and timeout. We don't get any option.
Oh, really?
Yeah, before coming display before displaying and it's time's up. We don't see any option.
Okay.
I can, but it's so
And internet going too much slow. I don't know.
Doctor. Doctor.
Okay, let's try the second question then. Okay, so nobody answered. Okay, because of timeout, right? Okay, okay, I understand. Never mind. Okay, let's see the next one. Second question.
It's still loading.
Doctor, still loading.
Okay,
Not
the correct
connecting.
answer is
No, it's still loading and time's up. Don't see any option.
okay, okay. Next time I will put a longer time. I think I put just 10 seconds because it's an easy question.
Now we
So let's
we
see.
don't get the
Okay.
option.
All right. So Rex is number 1. Pomad, you're number 2. Shafika is number 3. Only 5 people managed to answer. Okay.
No, we don't get the option to click.
Yeah, I understand. I understand because of the time, right? Maybe the okay. Understand.
And
Understand.
it's, yeah, it takes some time to load, and after that time, the time's up.
Okay. Okay. Never mind. All right. We move to next question. Okay.
Doctor, can you hear me?
Yes.
I cannot connect. I still connecting. Sorry.
Same here. Time's up. Your internet connection is slow, so you might experience delays.
Deep on the next one.
I think you're not going to be 1, 2, 3.
So we don't have to.
Okay. What is stimulated emission? The photon passes excited electron, then identical photon is emitted. Okay. So let's see. So who managed to answer?
And I'm in 11th position.
I didn't manage to answer.
Okay. We move on.
So it's not working. It's still loading. Time's up.
What determines a laser's application? The wavelength, also the output power. So let's see. Rex still number 1. Format number 2. Shafika is number 3. But then, okay, some of you could not access. So you still can't access?
No.
Still no.
No.
Oh, this is a bit unfair, right? Never mind, never mind. It's okay, we move on. We just continue playing. Okay, next question, number 5. What are common applications of lasers today?
No, we don't have this luck to attend this quiz.
Okay, time's up. The answer is all. Okay, you can use lasers in laser printer, DVD, CD, and also laser surgery. So let's see.
And they told me that.
First, Rex number 2, Shafika number 3. Okay. Okay, let's move to next question. Question number 6. What does LED stand for?
Light emitting diode. No current.
This very testing your responsive.
Okay, light emitting diode. LED stands for light. Some easy questions, okay? So who's at the top? Still Pomad, Rex number 2, Shafika number 3, Shaza, Belal. Try to catch up. Okay, ready? Next question. Number 7. What gives the color of the LED?
What gives
The type of gas inside it.
LED, right? This is LED.
Okay. Active element. Active element.
Pomad, Rex, Shafika, Shaza, Rosnita, coming up from somewhere. Okay, still many questions. Number 8, true or false? The longer leg of an LED is the positive terminal. True or false?
Really?
False. So we just see and just.
Oh, answer wrong.
Okay, Pomad, Shafika, number 2 now. Rex, what's happening? Shaza and Rosnita. Okay, let's move on.
Lumens per
What
watt.
is lumens per watt? In an LED, what is lumens per watt? Okay, time's up. Okay, Asif, coming up. Good, good. Question number 10, true or false? OLED stands for original light emitting diode.
এখানে মেডিকেল ছিল সার্টিফিকেট ওই মেডিকেল ছিল দেখছি এই ব্যাচ নাম্বার দেওয়া আছে তো এইখানে যা দেওয়া আছে আচ্ছা দাঁড়া সেফটি সব ঠিক আছে
Okay, time's up. OLED stands for organic light emitting diode, so it's false, okay? Asif, wow, coming up. Right, Rex, careful. Shafika, Muhammad. Okay, let's move on. Next question, 11. Light emitting diodes convert electrical energy to mostly time's up. The answer is 9. Okay, all of you got it right. So let's see. Shafika, wow. First place. Okay, let's see. Question number 12. Light from a blue LED has less energy than light from a red LED. Okay, the answer is false because light from a blue LED has less energy. No, blue is a shorter wavelength, therefore the energy is higher. So the answer is false. Wow, Pomad back to number 1. Rex number 2. Okay, let's.
Very testing your responsiveness.
13 out of 17. How does light energy travel? Okay, time's up. All right, radiation, right? The answer is radiation. Let's see scoreboard. Wow, Belal. Not bad, Belal. Okay, next question. 14. What does LIDAR stand for? Okay, the answer is light detection and ranging. Okay, so let's see the scoreboard. All right, Shaza coming back into the scoreboard. Plasmonic is the field that studies. The answer is A, the interaction between light and free electrons in metals. All of you got it right. Very good. Let's see who's in first place. Still Pomad, Rex, Shafika. Okay. Which is not an application of plasmonics?
Oh yeah.
Wrong answer, Rex.
I think I clicked wrong.
Okay, never mind. Okay, time's up.
Okay, correct.
The answer is it's not used in car manufacturing. Okay.
Yeah.
So let's see the scoreboard. Okay. Asif coming up. Can you be in first place? Last question. Graphene plasmonics have plasmon resonance frequencies in which regime?
Graphene. Wait. Graphene. Oh, yeah,
the answer is in infrared. Okay, it is in infrared. Okay, so Asif, number 3.
Thank you.
Rex at number 2.
Wow, 14. Muhammad.
Right, and Shafika is number 4 and Shaza is number 5. Okay. Okay. All right, just a simple quiz, and but since some of you could not access, that's fine. Maybe you can play some other time. time as well. Who could not access just now?
Yeah, mine is not working not at all. No question. 17 question is still not seen anyone. So have to enjoy.
Just for fun only, okay? It's just for fun.
Yeah.
Don't worry, all of you
Nah,
will get certificates.
this is interesting.
Right, but the winner will get first place, second place, third place. Will get winner certificate. The rest will just get participation certificate. Okay?
Okay, it's okay.
All right, just to boost you up because you know it's so boring listening to me talking. So just something to something for you. Okay.
Okay,
So that's all for my class today. I hope you learned something. And apologies for the technical problems just now. And I hope you had fun with Kahoot. You can go to Kahoot and try many different types of quiz there to test your knowledge. It's very fun. And if you have any questions, you can email me at Susi ukm.edu.my, or you can contact me, WhatsApp me 3608970. So feel free to drop me an email or call me, WhatsApp me if you have any questions about lasers, LED, plasmonics, or LiDAR. All right. Thank you for your attention, and apologies that I exceed about 30 minutes of the class. Okay, take care, everybody. Bye-bye.
Okay.
Bye.
Bye-bye.
Stay safe at home. Bye-bye.
Okay.